So in the incompressible limit, we have a problem with our standard approach to writing the weak formulation corresponding to the linear elasticity equations. And our solution approach will be to write the minimization of the energy potential in a different way. Now we're going to try and enforce this incompressibility constraint in a different sense. And we can either do this strongly or we can do this weakly. So in the incompressible case, well, in any case, we have the following two definitions for the stress and for the energy functional. And in the incompressible case, we know that the divergence of any solution U is going to be equal to 0. And so for any allowed U, which also means that from our energy functional, this term drops out. So we have, in a sense, a new energy potential. So we could try and enforce this constraint, the incompressibility constraint, directly in our minimization statement. The original minimization statement is that U is going to be the argument of the minimization of the infimum of the energy potential for all V. So what we could do now is in our search for different functions V, we can already say that we're only going to allow functions V such that the divergence of V is equal to 0. And in fact, that would be a perfectly fine statement. You would actually get a very similar statement to the one before. This would immediately give us the weak statement that the twice mu times epsilon V epsilon U and minus FV minus partial n Tn dot V, that's going to be equal to 0 for all functions V, but not all functions V in H1 0, but rather all functions V in the space of functions in H1 0 D such that the divergence of V is equal to 0, right? So that's a new set of functions, all functions in H1 D, the vector space of functions in H1, that also have divergence free, that are divergence free. And in a similar sense, if we were to now define this as a problem for U, we would say find U, but again, U is only allowed to be in that space. So that would be the same set of functions, such that that holds for all these test functions in that space. Now, that would actually be a perfectly fine weak statement, and in fact, it would be a coercive statement. This is, however, still not a statement that is very suitable for use in finite element applications. And the reason for that is this interesting space definition, right? So we're quite familiar with the H1D space. That's we can discretize that with Lagrangian basis functions without any issue. But now we're not looking for all these vector functions. We're looking for all these vector functions under this constraint, and that actually becomes very difficult to discretize. Yeah? It's very difficult to find a space that for which every possible entry in the space, every possible function in the approximation space is actually divergence free. So it's going to be very difficult to get a finite element approximation space that we can use for this weak statement. And hence, this is not really the weak statement that we want to use, even though, again, this is a perfectly fine way of defining the problem. So we're going to do this differently. And the way that we've essentially done this is a strong enforcement. Strong enforcement of constraint. Yeah, because it ends up being directly in the space. And whenever we prescribe something in the function space, this is called strong imposition. In a similar way, or the same thing holds for Dirichlet conditions. Dirichlet conditions are typically also strongly enforced, meaning that we're setting their values in the function space. Now, again, this is not very appropriate, so we want to do this differently, and instead we want to weakly enforce this constraint. So this ends up following from a different minimization statement. And I'll already just give you the statement from which this follows, and then we'll look into it a little bit better. So we're going to define U as the solution to still that argument of the infimum of all functions v in H1, 0. So I'm not going to add this additional constraint. So this is a function space that we're familiar with and we can discretize. But now I'm going to do something else. I'm going to say it's going to be the minimizer of something that maximizes of our energy, but now with an additional term, namely Q times the divergence of V. So again, we see somehow an inf-sup statement here, and even though we're gonna read this in the same way as we've done before, this has in principle nothing to do with the inf-sup statements that we saw before. And those were conditions for well-postness. These are just originate from the physics, trying to get a minimizer of an error potential or an energy potential. So what does this sup now mean? Where does it come from? I'll write this a bit clearer. So the way that we read this statement is again from the outside inwards. So we're going to take a function v, a vector valued function v, and then I'm going to perform the inner operation. Then I'm going to take the supremum over all q of this operation. And this operation is just going to give me a value for a given v and a given q. And I fixed v at this point. So I'm going to loop over a whole bunch of different q's. And in principle, I'm going to loop over infinitely many q's. And I'm going to find the maximum of that expression. And once I've done that, I'm going to choose a different v. And again, I'll perform whatever is in these large curly braces, and I'll get the new maximum. And I'll do this for every possible function v in that space H1D. Now, again, there's infinitely many functions in that space, so we would, in practice, not be able to do this, but in principle, you would do this for infinitely many functions. And for each function, I obtain a value. And the final statement is that u is now going to correspond to the function for which you obtain the minimum of all these values. Okay, so why is this the same thing as what we have done before? Now, that's due to this trick in the way that the incompressibility constraint now shows up. Essentially, there are two cases. One case is where the divergence of v is not equal to 0. And one case is where the divergence of v is equal to 0, right? In principle, I can subdivide my functions in these two sets. Any function in H1D is either going to have vanishing divergence or it's not. It's either going to be incompressible or it's not. So for all cases where the divergence of v is not equal to 0, the supremum of, well, whatever, well, I'll write this out, E of v plus q of divergence v is going to be equal to infinite. This is going to be infinitely large because I can always choose q to be equal to c times the divergence of v. I'll substitute that in there, and then I'm going to choose c to be infinite. You know, I can always limit. I can always make it larger and larger and larger and larger. Yeah, and the result is going to be if the divergence of v is not equal to 0, then this integral is going to give me an infinite value, irrespective of what this is. For a fixed v, that's fixed, but this addition is going to be an infinite addition, meaning that the supremum is going to be infinite. For every function that is divergence-free, the supremum of EV plus Q divergence of V is simply going to be, well, EV. So clearly, if I now run over all my possible functions V, then all of these are immediately excluded because they give me infinite values, and that's never going to be the infimum. Yeah, so naturally from that addition of the supremum, we are forced to only consider functions that are divergence-free. And for these functions that are divergence-free, I simply retrieve the argument of the infimum of EV. And that was precisely the original statement here, that we're looking for an argument of an infimum of divergence-free functions of EV. And that's ends up what this then says. Okay, so this seems like just a trick. I haven't really done anything. In the end, I obtain the same solution. Well, yeah, that's precisely the point, right? We want to obtain the same solution. The thing that we don't want is to have to enforce this condition in the space. And now this condition sort of follows naturally from this inf-sup statement. Now, how do we now use this as the basis for obtaining a weak formulation? Well, we have to make a couple of observations. So the first observation that I'll try to motivate is that, you know what, I'll first rewrite this. I'll call this EV plus the integral of the Q times the divergence of V. I'll give that a new name, J, which now depends on V. And on Q. Yeah, so this is a this is linear. No, it's actually not linear. Is it not linear? No. Okay, this is a functional that takes two expressions. It's actually not linear in terms of Q. Okay, but nevertheless, it's a functional. If I have a function V, a vector valued function, and if I have a function Q, which is also a function just in L2, then this will give me a value and nothing else. So the first statement that I'll make is that the infimum of the supremum of J, and again the supremum over Q, and the infimum over V, that is going to be equal to the supremum of the infimum of J. Well, again, the infimum is over the functions V, and the supremum is over the functions Q. So, does this make sense? What does this say on the left here? And again, we have to think of this with brackets. So for a given function v, if it's divergence free, this is either going to be infinite or it's going to be equal to the answer of my star equation. You know what, I'll call this one this is the star equation. Yeah, so that's the solution that we obtain if we have prescribed that all our functions are divergence free. Yeah, so that's the problem that we're actually trying to solve. Yeah, so the left part of the equality here is either going to be infinite for certain values, for certain expressions of v, and if it's not equal to infinite, it will correspond to it will give me the solution to the true optimization problem. Yeah, sorry, I confused me myself for a second here. Which means that in the end, this is going to give me that, right? Because it's going to give me the infimum of the two. Yeah, so that value is going to be the same value if you substitute the true solution in there. So what happens here on the right side? We take the infimum of JVQ. Well, there's two options here. Either we have also a divergence-free solution in here. Yeah, let me say it like this. Okay, now let me. This is pretty complex theory, and having to explain this clearly is often a challenge. Okay, so the one on the left we know is gonna give us the solution to the true optimization problem. The one on the right, we can do two things. For any function q, I'm going to perform the interior thing, which means that either for a certain function q, I can substitute my solution u and get the solution star. And I'm trying to get the minimum here. So I can always get the solution star for any q, because for the solution star, this additional term here drops out. Yeah, so that okay, yeah, maybe I should try it like this. Yeah, I don't know why I'm introducing the star. I feel like that's just getting things more complicated. Either I get E on the left, on the left I get E, the energy of the true solution. Yeah, that follows from what we said over here. On the right, for any q, this infimum is either giving me E of u. Yeah, because at that point I have a divergence-free solution, so this term drops out, so it becomes independent of q. Or if I have a different q for which I can actually get a lower infimum, then I'll get something that is larger than EU, or smaller. Sorry, because this is in the inside is the infimum. Yeah, so I either get the actual energy corresponding to the solution, or I get something that is smaller. So now I'm taking the supremum over all possible q's. So that's then going to give me, as a maximum, it's going to give me that one. Yeah, and that's why these two are equal. So the point here being I can swap the inf and the sup, and I will still get the same expression of this new potential j. So this swapped version, however, gives us a new variable to define. Yeah? We called our solution u we defined our solution u to be the argument of inf-sup. And now I also have a sub-inf, so I can define a new variable, which I'll call p, and we'll see in a second why, which is equal to the argument of the supremum of the infimum. Of JVQ. Yeah, so I've sort of formulated what to call a dual problem, and thereby introduced a new solution variable. Yeah, and given that U is going to be the solution of the infimum of the supremum, and P is going to be the solution of the supremum of the infimum, I can also say that here on the right side, this is going to be equal to J of U, comma P, the two solution variables. Okay, so what I can do now, and again we have to work from the outside inwards with these conditions, these inf-sup conditions or sub-inf conditions. But I can already substitute my known solution on the outside. Again, the way that we read this is we're going to loop over all possible functions v, or we're going to loop over all possible functions q, and get a certain expression. I know that this one is going to give me u as an argument. So the argument of this one is going to be u. And I know that the argument of this one, well, I just defined it, that's going to be p. So I can actually choose that function. I can choose this function u here, and I can choose the function p here. And then I'll perform the interior expression. So then this one becomes that the supremum, where I've now chosen v to be equal to u, of j u comma q, the supremum over all q, is going to be equal to, well, here we have the thing all the way on the right, j u p. And it's going to also be equal to, well, this statement here is sub-inf, where I've now substituted my known argument, which produces the supremum, as p, giving me a leftover statement inf of v of j v comma p, because I've substituted in place of q, p. And this one is pretty straightforward to rewrite. If where I have my middle statement u comma p, and if the supremum over all possible functions q is going to be equal to that, that means that any other choice is going to be smaller than or equal to that for all q. And similarly on the right here, if the minimum value of this guy for all possible functions v is going to equal, well, this statement, then that means that any other choice of v is going to be larger than or equal to. And this has to be true for all functions v in, well, h10d. And the reason why I'm showing you this is that now we see this chain structure, something being smaller than our true potential at the solution point for all q, and being smaller than, or being the minimum of all choices of v. And this is why we're calling this a saddle point. So if we compare that to typical minimization problems, then you're kind of only looking at this side of the statement. And for a standard minimization problem, if I try to draw this in 2D, then you would have, I don't know, some potential that depends on two variables in this drawing that might have a certain minimum at some point and then grow outwards. Yeah, so then you're searching for that minimization, that minimum point. Whereas for a saddle point problem, you get something that would look like your typical saddle structure. And on one of the diagonals you would get a solution field that kind of looks like that, and on the other diagonal you get a solution that looks like that, and that's why this is called a saddle point problem. Yeah, and these points, the point here is now characterized by this statement, and that's why this is a saddle point problem. Okay, so again, how do I now obtain a weak statement from this? It's nice that we call this a saddle point problem because of this, but how do we get a practical method from this? Well, this is actually two inequalities, two minimization problems, one on the boxed in red and another one over here. So I actually get two weak statements. Let me start with the one on the right. So what we obtain here is that if I take the Gateau derivative around u, then that's going to equal to 0, right? Because any other choice of u is going to give me a larger value. So that means that d epsilon of j u plus epsilon v comma p is going to be equal to 0. And the second problem is the one on the left, and that's a very similar problem. So we can write the delta of j u p plus del q at del is equal to 0 is also going to be equal to 0. And the first one has to be true for all choices of v, and the second has to be true for all choices of q. Now what was j? Let me just repeat it over here. For some arbitrary set of functions, v and q. And let me take the particular choice of body force being equal to 0, and we also don't have attraction, just for simplicity. So then we had this. Oh, a little too fast. No, that's also not correct. So this. And then we had this additional term. Did I write it with a plus? Doesn't matter. It'll be consistent. Yeah, plus. That's how we define j. So now I can obtain these Gateau derivatives, and that means that our first statement is going to be that P v is equal to 0. Now, so what I've done is I substituted u plus epsilon v in here, and in here, and in here. And then I take the derivative with respect to epsilon, so that removes the square term on u here, and it removes the u term here. And then you substitute the epsilon is equal to 0, and that removes the square term on v here. And that's why I left with the cross term here, should actually still be a 2, plus p times the divergence of v, and that has to be true for all v. So how about the second equation? Well, we're substituting p plus del q in here. So where does that end up being? Well, it just shows up here, right? Then we take the derivative with respect to delta. Well, this one becomes independent of delta, so that one drops altogether. And then we substitute delta is equal to 0. So we actually only are left with q divergence of u, yeah, because we've substituted u in place of v. Okay, and that's pretty much the conclusion right now. These are the new weak statements. This is the mixed formulation for a linear elasticity problem under the incompressibility constraint. And I hope that you recognize this equation, because this is precisely the Stokes equation. Yeah, so it was not a coincidence that I took this as an example. So what does that mean? Well, the Stokes equation shows up in both fluid mechanics and solid mechanics. In fluid mechanics as the Navier-Stokes equation under the assumption of very slow moving flow, very creeping flow. And in solid mechanics it shows up as an incompressible solid treated in a mixed formulation. Now, mind you though, the fields mean something different though. In fluid mechanics, U is a velocity field, whereas in solid mechanics U is a displacement field. Probably underline again that these are vector fields. Yeah. Yeah, so it's the same partial differential equation, but it has a different meaning in both these fields, but we can also derive it from the same perspective. So what are the takeaway points here? The takeaway points are that we ended up finding, or we found a problem for which our typical minimization was not appropriate. So we changed the way that we described the physics. We changed our minimization problem. Now we use this trick with the inf-sup to obtain a natural way of incorporating our constraint instead of having to bake it into the space. That was a trick right here. That introduced now a new solution variable, making this a mixed formulation. And this is something that we can actually use to also treat the case of the limit case of incompressibility. Now, of course, we know from our lectures on inf-sup stability and also from the introductory lectures that we have to be very careful in our choices for our pressure space and our velocity or displacement space. Yeah? And we'll get back to that in maybe not the next video, but the one after that. Yeah? We'll start to look at the different spaces that are appropriate or are not appropriate. I guess the last thing that I would like to point out, just for those of you who are familiar with this terminology, is that the pressure now has shown up as the Lagrange multiplier corresponding to the incompressibility constraint. Yeah? So we have to add in a constraint, and that introduced this dual problem for which we denoted now as a solution P. So that is actually how the Lagrange multiplier is defined, and for the incompressibility constraint, the Lagrange multiplier is the pressure. Yeah? So that gives sort of a very mathematical interpretation to a quantity that seems so physical, right? That pressure, but from this approach to deriving these equations, we see that goes hand in hand, right? Again, the math and the physics go hand in hand. Now, I think in the next video I'll give one more example of a constraint minimization problem. Just to do this a couple of times so that you're slightly more familiar with the line of arguments here. I'll go probably a little faster though. And in the videos after that we'll start talking about these spaces. Yeah. So, thank you for your attention and see you in the next video.